Halogenoalkanes are useful compounds in synthesis. A reaction pathway is shown. So we can see that we've got a compound at the very beginning there with a halogen and an alcohol group, so a Br and an OH, and then that Br has become, if we look, has become an OH, and then our compound has changed and they've gone to molecular formula. So it might be helpful to add up the carbons in our original. So we've got 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens and 2 oxygens. So we can see that when we go from the top there in reaction 2 to the bottom, we've lost 4 hydrogens along the way. And then we're going reaction 3 to Z. Okay, so it says give the IUPAC name for the first compound. So we're having a look at it. Let's just sketch it out maybe. So I'm not going to put all the hydrogens on because this sketch is just to help me name. But if we look at this and we start numbering, so remembering that the alcohol here is a higher priority functional group than the bromine. So we're going 1, 2, 3 along there. So we're going prop. There aren't any double bonds between the carbons, so we're going AN. And then the alcohol is on the first carbon, so propan 1-ol. And then what we're doing is we are having a look and noticing that we've got a methyl group on number 2 and a bromine on number 3. Now, remembering we put them in alphabetical order, so we're going to have to go the bromo first. Now, technically, we wouldn't need the number 2 for the methyl group because on a 3-carbon chain, there's nowhere else you can put it, but you wouldn't be penalised for saying 2-methyl for that structure. Then it says that reaction 1 occurs via nucleophilic substitution. Why are halogenoalkanes attacked by nucleophiles in this way? So the point is that nucleophiles are electron pair donors and that they always attack delta plus carbons. So why is there a delta plus carbon in a halogenoalkane? Well, in this one, Br is more electronegative than carbon. Creating a polar bond. Oops. So if we have a look, C, Br, we've got delta minus there, delta plus here. Which means the lone pair on the nucleophile can be donated, because the definition is it's a donor, to the delta plus carbon. And then it says the infrared spectrum of compound Y. So you go to table A on the data sheet and you look this up, 1680 to 1750, and it says it's a C double bond O bond. Now remembering that compound Y, if we just scroll back, compound Y was C4H6O2. So we'd lost quite a few of our hydrogens from our compound that we had before, which, remembering our compound that it was coming from had a methyl group on number 2, and we'd nucleophilically substituted the Br for an OH. So this was our compound we were making it from, and now we've lost 4 hydrogens and we've got C double bond O. So thinking about where that could happen, a C double bond O would come from a C single bond O. So these single bond O's might change to double bond O's, but we've also got to lose 1, 2, 3, 4 hydrogens. So we can see how that might happen. And we want to draw the displayed formula, so we mustn't miss out any atoms or any bonds, which means that up here I do need to draw out my methyl group. So you never really affect the R group, the chains. But we're changing the single bonded OH to a double bonded O. We're keeping one of the hydrogens, but losing one of the hydrogens. off the carbon and 1 off the OH. And then it says Z has the empirical formula, C3H4NO. Now remembering it's coming from Y here, and it tells us anything else, it just tells us it's coming from Y. We're keeping an oxygen and we're adding nitrogen, but for some reason the carbons are changing. But this, remember, is an empirical formula, so the likelihood is that our actual formula is probably going to be double that, C6H8N2O2, because we had 2 oxygens before and we had 4 carbons. Now you have to draw on your knowledge. This is quite a hard question, but you have to draw on your knowledge of aldehydes and ketones. This was an aldehyde. And the reactions we know of aldehydes and ketones is we can either turn them back to alcohols or we can turn them to hydroxy nitriles. And given the presence of an N, that's what we're looking to do. So remembering that we're keeping the methyl group part, we can't really change that. And then we had the C's. Now we're going to add a C triple bond N and turn it into a hydroxy nitrile. We're going to repeat that on both sides, and if you double check the formula, you'll see that this meets the requirements of our formula. And then it asks us what the reagent would be. So what we need to remember is that this is the reaction that has KCN followed by a dilute acid, such as HCl.